Hello! We are going to talk about functions today. Do you know what's a function? You will in a few moments. So, suppose you have two sets, A and B. They could be sets of numbers or not. They could be sets of anything. It could be a set of feelings. A could be the set of with the following elements: love, hate, and shame. 3 feelings. Okay, that's fine. Elements of a set could be other sets, so it could be getting complicated. Just for simplicity, we are going to give examples about sets of numbers, but we are going to be looking at the definition of a function. What's a function? A function from a set A to a set B. So we have to tell where it goes to where. So A is what we call the domain of the function. Set B is what we call the codomain of the function. And we say the function maps each element of A to one element of B. Okay? So important here is that every element of A is associated to some element of B. Okay? So if I were to make arrows detailing, so for each element of A, there's an arrow going out. So it's like each element of A is traveling to some point of set B. Okay? So that's why we say the function A maps or takes elements of set A into elements of set B. Okay? So when you look at A, each point has one and only one arrow going out. Always. Okay? If it has 2 arrows, it's not a function anymore. If there's an element here with no arrow, this is not a function anymore. To be a function, you have to have each element of the domain with exactly one arrow going out. As for elements of the codomain B, it doesn't matter. You are free. You could have elements of the codomain with no arrows, elements with a single arrow, elements with multiple arrows. That's okay. These are all okay with the definition of a function. All right? So, we could, to define a function, we could make a diagram like this, or we could say where each particular value of A goes, or we can give a formula. But don't be trapped. Many students think only formulas define functions. That's not true. I'll give some examples in a second. We can perfectly define a function without a formula, but usually we have a formula, okay? So, and when we do the elements of set A, the elements of my domain, little a belonging to set A, elements of my domain, we call this variable that runs on the inputs of the function, or the independent variable, or the argument of the function, these values of A. And then we calculate B. B is the function evaluated at A. Are the outputs. The values of B are the outputs of the function. We think of the variable B as the dependent variable, or we think of f of calculated A as a value of the function. Okay? So that's how we talk about the terminology to talk about what happens in the codomain in set B. So here in my domain I have inputs, independent variables, argument of the function. In the codomain I have outputs, dependent variable, values that the function takes. Okay? And we say that the function maps an element of the domain to some element of the codomain. Alright? So what's f calculated in A? A is a set, it's not a number. So that is the value that the function takes. And these are elements of my codomain, such that this little a is some element of the domain A. Okay? So we let this little a run along all elements of A, and we see where it goes. And we collect all the points of the codomain where the points A are mapped to. We call this the range of the function, or the image of the function. Okay? So f of A is the range, and the range is a codomain of, it's a subset of the codomain. This set here is a subset of the codomain. When they are equal, and only when they are equal, we call the function surjective. We're going to give an example in a second, but before that, a little bit more of notation. Let's talk about the inverse image of some element of the codomain. Okay? And we put a -1 here. That's not 1 divided by this. Like I said, this f of b might not even be a number. So this is just a notation for all the elements of my domain, little a, that when I apply the function to this little a, I go to this point b. Okay? So, example. It will be much easier if I give an example. Suppose set A is the set with the numbers 1, 2, and 3. So say A is the set with 1, 2, 3. B is the set with the numbers 4, 5, and 6. Okay? So I can write here, my B has 4, 5, and 6. These are 3 elements of my set B. The function f maps 1, this element of the domain, 1, to 4. So f of 1 is 4. It maps 2 to 4 also, f of 2 is 4. Maps 3 to 6, f of 3 is 6. Okay? So that's what the function does. This set is the domain, this set is my codomain. What's my range here? So my range has four and 6. The range is not equal to the codomain. The codomain has the 4, 5, and 6. The range does not have 5. So this function is not surjective. Okay? Now, how about inverse images? What's the inverse image of number 4? What are all the points of my domain that are mapped to 4? Well, 1 goes to 4 and 2 goes to 4. So the inverse image of 4, it's going to be 1 and 2. The inverse image of 5, who is mapped to 5? Nobody. No element here goes to 5. So that's just the empty set, and we usually denote the empty set like this or like this. Empty set, another notation for the empty set, okay? What's the inverse image of 6? What are the elements of my domain that are mapped to 6? Only the 3. So this is. So the inverse image can be a set with many elements, the empty set, a set with a single element. Okay? But in all cases, it's a subset of my domain, the inverse image. All right? Come with me. And here we have a function f going from A to B. Pick a subset of my domain. So D is a subset of A. Okay? What's f of D? Well, I look where all the points belonging to D are mapped. So suppose this point goes here, this point also goes here, and this point goes here. Okay? And these points go elsewhere. So when I map the set A into set B, the points in D, they go to this subset here. So that's f of D. It's a subset of the range, a subset of the codomain also. Okay? So f of D are all the values f of D in the codomain such that D runs along all points of the set, subset D of the domain. Okay? Good. When is a function injective? Now let's look at this important idea here. Injective functions. Well, we usually have 2 ways to define injectiveness. If you pick 2 different points of my domain, they have to be mapped into different points of my codomain. So if A1 is different than A2, this implies that f of A1 is going to be different than f of A2. Okay? Or we can think in terms of the contrapositive. What's the contrapositive? This implies that. The contrapositive is not this, implies not that. So what's the negative of f of A1 different than f of A2? The negative of this statement is Well, they are equal. And what's the negative of this? A1 different than A2? Well, the negative is that they are equal. So that's another way to say the same thing. That's why they are equivalent. Okay? If 2 points of my domain go to the same point of the codomain, it's because they are already the same point to start with. Okay? Examples here. A bunch of functions from real numbers to real numbers. The first one is f of x is 2x. So that's, the graph is a straight line. Every point that you have in your real number, we can get half of it. So each point of my codomain will be reached by some point of the domain. So this function here, and different points of the domain will be mapped into different points of the codomain. So if x1 is different than x2, twice x1 is going to be different than twice x2. Therefore, this function is both injective and surjective. Injective and surjective. So this function is both injective and surjective. We call the functions like that bijective. Okay, they have the two properties. How about f2? The function takes the square. So I plot the diagram of f2 here. If I have two different points, for instance, -3 and 3, they go to the same point of the codomain. They are mapped to the same point, right? F of -3 is -3 squared, which is 9, which is equal to f of 3. So that in this case of f2, this function f2, this function is not going to be injective. And it's not going to be surjective because who goes here in -2? -2 is not the square of any real number. So this function fails everything. Okay? So this function here, not injective, and it's not surjective. Okay? So bad function x squared. You could notice that I could do some trick here. I could change my domain, my codomain, so instead of all real numbers, I would have just the non-negative ones. And then the function would be surjective. But if you change your codomain, you're changing the entire function. Okay, that's the thing. The function is made, the definition of the function has to include the domain, the codomain, and the way we map points of the domain to the points of the codomain. If I change my codomain, I'm changing the function actually. Okay? So next, f3 is 2 to the power x. And here I have the graph of that. So if I have two numbers, some x1 and x2, and if they are different numbers, well, say the x1 is smaller than x2, when I apply the function, f of x1 will be smaller than f of x2. This height here is smaller than this height here. Okay? So this function here is going to be injective. Yes. But how about surjective? Can this function take any real number? Not really, right? If I pick a negative here, -1, for instance, nobody will be mapped into -1. No real number, at least, no point of my domain, no real number will be, when we apply the function, will go to -1. So this function is not surjective. Okay? So it's injective, but not surjective. This is both, this is neither, this is injective but not surjective. How about this function f4 here? f4 of x is x times x minus 2 times x plus 2. I draw the diagram here. When x grows very large, the function becomes very, very positive. When x goes to minus infinity, the function becomes very, very negative very fast. This function equals 0 at -2, 0 and 2. So this function here is not going to be injective because I have different points of my domain that when I apply the function to these points, I get to the same point of the codomain. So this function is not injective. Okay? Is it surjective? If I pick any point here, very negative or very positive, yes, I will be able to find. If I pick a positive number, I can pick some value here, very large, that when I apply the function, I get to this. And the same here, I can always find a point here that when I apply the function to this point, I get this value. So no matter which value I choose positive on the y-axis, on the vertical axis, I can always find a value on the horizontal axis, an x, such that f4 of x equals y. Okay? So this function here, it is surjective. But not injective. Okay? So that's only surjective, not injective. And this one is only injective but not surjective. F2 is neither, and F1 is both. So all combinations, in principle, these two properties are independent properties. One property can hold and the other fail, or both can hold or both can fail, any combination. Okay? So that's the basic definitions of functions. I hope you enjoyed my video. See you next time. Bye bye.